Hey, sleepers. Tonight, we're going to chase a ghost in the machine of the universe. Imagine a tiny spark, a whisper of light that doesn't just race across space, but outruns time itself. It's a phantom particle. A what if written in the language of mathematics. It is a whisper from a world that may not even exist, a world that runs on different rules, a world just beyond the veil of our understanding. So before you get comfortable, take a moment to like the video and subscribe. It helps our little corner of the cosmos reach other curious minds. And while you do, feel free to share your location and your local time in the comments. It's always wonderful to imagine all of us, scattered across the globe, listening together under different skies, united by a shared curiosity. So close your eyes, take a deep breath, and get ready to drift off as we explore the particle that travels back in time. Let us begin our journey with a simple thought, a thought about speed. In our world, there is a speed limit. It is not written on a signpost on the side of a highway. It is woven into the very fabric of reality itself. This is the speed of light. It is the ultimate velocity, the fastest anything can travel. A universal constant. Light travels at about 186,282 miles per second, or nearly 300,000 kilometers per second. It is so fast that a beam of light could circle the Earth more than 7 times in a single second. For us, on our human scale, it is practically instantaneous. But in the grand cosmic theater, it is a finite, measurable pace. Nothing, according to our deepest understanding of physics, can break this speed limit. Nothing with mass, anyway. But what if there was a loophole? What if there was a particle that lived its entire existence on the other side of that barrier? A particle born faster than light, forever destined to outrun it. This is the idea of the tachyon. The tachyon is a hypothetical particle. That word, hypothetical, is very important. It means it is an idea, a prediction, a ghost in the beautiful mathematics of our universe. No one has ever seen a tachyon. No one has ever measured one. It exists for now, only on paper and in the minds of physicists who dare to ask, what if? The word tachyon comes from the Greek word tachys, which means swift, and a tachyon would be swift indeed. It would live its life in the fast lane of the cosmos, a place where our rules of physics seem to turn inside out. Imagine you are pushing a toy car. To get it moving, you need to give it a little push, a little bit of energy. To make it go faster, you need to push it harder with more energy. This is how our world works. The more speed you want, the more energy you need. This rule is a cornerstone of Albert Einstein's theory of special relativity. As an object with mass, like a spaceship or a baseball or even a single atom, it's closer and closer to the speed of light. It requires more and more energy to speed it up. Its mass effectively increases. It gets heavier and heavier from the perspective of someone watching it. If it were ever to reach the speed of light, its mass would become infinite. And to move an infinitely heavy object, you would need an infinite amount of energy. Since there is no infinite source of energy in the universe, the speed of light remains an unbreakable barrier. A cosmic speed limit for all of us, for everything we know and can touch. But tachyons, these ghostly particles, would play by a different set of rules. They are imagined to have a property that sounds like something from a fantasy novel. They have imaginary mass. Now, this doesn't mean their mass is make-believe in the way a unicorn is. In mathematics, an imaginary number is a very real concept. It's a number that, when multiplied by itself, gives a negative result. Think about that for a moment. We learn in school that a negative number times a negative number equals a positive number. And a positive number times a positive number also equals a positive number. So how can any number, when squared, be negative? Mathematicians invented a new type of number to solve this puzzle, based on the square root of -1. They called it I for imaginary. It opened up whole new worlds of mathematics, allowing us to solve problems we never could before. It is a number that steps sideways from the familiar number line of positive and negative. So, when a physicist says a tachyon has imaginary mass, they are using this mathematical tool. It's a way of describing something that behaves in a profoundly strange, almost opposite way to normal matter. For a tachyon, the rules of energy and speed are flipped upside down. A tachyon is born faster than light. It can never, ever slow down to the speed of light. That would be its unbreakable barrier, just as light speed is for us. To slow a tachyon down to the speed of light would require an infinite amount of energy. And here is the most curious part of all. As a tachyon speeds up, as it goes faster and faster, its energy decreases. Think about that. In our world, we burn fuel, we use energy to go faster. A tachyon would do the opposite. It would lose energy to accelerate. A tachyon, at its lowest energy state, would be moving infinitely fast, zipping across the entire universe in a single instant. It's a completely backward concept to our everyday intuition. It's like a car that gains fuel the faster it goes, or a bicycle that is easiest to pedal when you're going at 1,000,000 miles an hour. It is a beautiful, strange, and perfectly logical outcome of the same equations that gave us the cosmic speed limit. It's a hidden door in the mathematics, and on the other side of that door is the land of the tachyons. For now, we have only peeked through the keyhole. We have seen a world that might be possible, but we have never been able to prove that it is real. The tachyon remains a ghost, as swift and silent. What if? The idea of particles moving faster than light is not entirely new. It did not spring fully formed from a single mind in a single moment. Like most great ideas in science, it has roots. It is a seed of a thought that was planted long ago and nurtured by many curious minds over the decades. The story of the tachyon is a story of looking at the accepted rules and wondering, is that all there is? One of the first to peer into this strange possibility was the German physicist Arnold Sommerfeld, a true giant of theoretical physics in the early 20th century. Sommerfeld was not just a brilliant scientist in his own right. He was an extraordinary mentor. He supervised an incredible number of future Nobel Prize winners, people like Werner Heisenberg and Wolfgang Pauli, who would go on to shape our understanding of the quantum world. He had a gift for seeing potential, for pushing his students to explore the deepest and most challenging questions. Around 1904, even before Einstein had fully published his theory of special relativity, Sommerfeld was already exploring the mathematics of objects moving faster than light. He recognized that the existing theories of the electron, when pushed to their limits, seemed to hint at this possibility. He was one of the first to publish a paper seriously considering what would happen if something could break the light barrier. At the time, it was a purely academic curiosity, a mathematical game, but it was a seed. Sommerfeld had cracked open the door, just a little, to let future generations peek through. For many decades, the idea remained mostly dormant, a footnote in the grand story of relativity. Einstein's theory was so successful, so powerful in explaining the universe, that the idea of anything violating its central speed limit seemed like a fantasy. It was considered a flaw in the equations, a mathematical oddity that didn't correspond to physical reality. Like finding a solution to an equation that tells you a house has a negative number of rooms. Mathematically possible, perhaps, but physically meaningless. The consensus was that the universe simply did not allow for faster-than-light travel. End of story. But science is never truly the end of the story. It is a continuous conversation. And in the 1960s, a new generation of physicists began to question the old consensus. One of these was an American physicist named George Sudarshan. Born in Palam, India, Sudarshan was a brilliant and sometimes overlooked figure in physics. In 1962, he, along with his colleagues, published a foundational paper that laid out a consistent theoretical framework for particles that always travel faster than light. They showed how such particles could be incorporated into quantum theory without immediately breaking everything. They explored the strange properties of these particles, the upside-down relationship between their energy and speed. They had essentially built the first complete blueprint for a tachyon. Their work was rigorous and profound, but it didn't make a huge splash outside of theoretical physics circles at the time. Then, in 1967, another American physicist, Gerald Feinberg, independently revisited the idea. Feinberg was working at Columbia University, and he was fascinated by the symmetries and possibilities hidden within the equations of relativity. He published a paper titled Possibility of Faster-than-Light Particles. It was in this paper that he coined the name that would stick. He wanted a name that captured the essential nature of this hypothetical particle, its incredible speed. He turned to the ancient Greek language, a common wellspring for scientific terms. He took the word tachys, meaning swift or fast, and created the term tachyon. It was a perfect name, catchy, evocative, and scientifically rooted. Feinberg's paper, perhaps due to its catchy new name and the cultural mood of the 1960s, a time of questioning authority and pushing boundaries in all areas of life, captured the imagination of the wider scientific community and even the public. The tachyon was born not as a physical discovery, but as a fully formed concept. Feinberg, like Sudarshan before him, was not trying to prove that tachyons existed. He was a theorist. His job was to explore the limits of the possible. He saw a solution in the equations of special relativity that everyone else had dismissed as non-physical. Where others saw a bug, he saw a potential feature. He asked, what if the universe uses this solution? What would that look like? How would it behave? He explored the strange consequences, including the idea that tachyons could have imaginary mass and that they would speed up as they lost energy. He had taken the ghost that haunted the edges of relativity and given it a name and a set of characteristics. He made it something that other scientists could talk about, argue about, and even, eventually, search for. The tachyon was no longer just a mathematical artifact. It was a candidate particle, a challenge to the established order of the cosmos, a swift and silent question mark hanging in the universe. And it all started because a few curious minds refused to believe that the story was over. To truly appreciate the strangeness of a tachyon, we need to spend a little more time with the physics of faster-than-light travel. Let's gently wade into the waters of Einstein's special relativity, not to get lost in the currents of complex math, but to feel the gentle pull of its core ideas. Imagine the universe is a vast, calm lake. The surface of this lake is what we call space-time. It is a four-dimensional fabric, weaving together the three dimensions of space, length, width, and height, with the fourth dimension of time. Everything in the universe, from you and me to the farthest galaxy, exists and moves on the surface of this lake. Now, imagine a boat on this lake. This boat represents any object with mass, what scientists call a bratyon, or, more simply, partyon. This comes from the Greek word brades, meaning slow. This is us. This is the matter we are made of. When our boat is still, it just bobs gently in place. To get it moving, we need to start the engine. We need to use energy. As the boat moves faster and faster across the lake, something strange happens. It starts to create a wake. This wake is a disturbance in the space-time lake. The faster the boat goes, the bigger the wake becomes. In physics terms, the object's mass increases. It's not that it's actually getting more atoms, but its resistance to further acceleration grows. It gets heavier in a relativistic sense. Now, imagine trying to get this boat to move at the speed of light. The speed of light is like a special magical speed on this lake. It is the speed at which the ripples on the lake itself travel. As your boat approaches the speed of the ripples, its wake would grow to an infinite size. It would effectively have infinite mass. To push an infinitely massive boat would require all the energy in the entire universe, and then some. It's impossible. So the speed of light is the ultimate speed limit for any boat, for any object made of ordinary matter. The lake of space-time itself forbids it. This is the first kingdom of particles, the kingdom of the slow particles, the bradyons. We live here. There is another kingdom, the kingdom of particles that have no mass at all. These are called luxons, from the Latin word lux, for light. The most famous luxon is the photon, the particle of light itself. Because they have no mass, they are born at the speed of light, and they will only ever travel at the speed of light. They are the ripples on the lake. They cannot slow down. They cannot speed up. They are the constant, the benchmark, the cosmic speed limit made manifest. This is the second kingdom. But the mathematics of relativity, the very equations that describe our space-time lake, hint at a third possibility. A third kingdom. This is the kingdom of the tachyons. A tachyon is not a boat on the lake. It's something else entirely. Perhaps it's more like a creature that lives underneath the surface of the lake, in a different medium, where the rules are different. It is forever separated from us. It is born moving faster than the ripples on the surface. For a tachyon, the surface of the lake, the speed of light, is an impenetrable barrier from below. To slow down and reach the surface would require an infinite amount of energy. So, it is trapped in its faster-than-light realm, just as we are trapped in our slower-than-light one. This is where the idea of imaginary mass comes into play. It's the mathematical description of this upside-down world. Let's try another analogy. Think of energy as money. In our world, to buy speed, you have to spend your energy money. A little speed costs a little money. A lot of speed costs a lot of money. Approaching the speed of light costs an infinite amount of money. You can never afford it. But in the tachyon world, it's the opposite. A tachyon is born with a huge amount of speed, but it is deeply in energy debt. The faster it goes, the more it pays off its debt. Its energy gets lower and lower. An infinitely fast tachyon would have zero energy. It would have finally paid off its entire cosmic debt. But to slow down, to get closer to the speed of light, it would have to go deeper into debt. It would have to accumulate more and more energy. To reach the speed of light from the other side would mean taking on an infinite energy debt. It can never afford it. So we have these three distinct realms, all described by the same elegant theory. The world of the slow, where we live. The boundary of light, where photons live. And the hypothetical world of the swift, where tachyons might live. They are like three different countries with a shared border that is impossible to cross. We are in the land of less than light speed. The photons are on the border itself. And the tachyons, if they exist, are in the land of greater than light speed. This strange, inverted relationship between speed and energy is the physical heart of the tachyon concept. It's what makes it so counterintuitive, yet so compelling. It's not just about going fast. It's about a fundamentally different way of existing in the universe. A way that is, in a very deep sense, a mirror image of our own. It challenges our most basic assumptions about effort and reward, about cause and effect. And it is this challenge that leads us to the most mind-bending implication of all, the possibility of sending a message back in time. Now we arrive at the very heart of the mystery. The reason the tachyon is not just a scientific curiosity, but a concept that shakes the foundations of our reality. The connection between faster-than-light travel and time travel. This isn't a flight of fancy from science fiction. It is a direct, logical consequence of Einstein's theory of special relativity. And to understand it, we don't need complicated equations. We just need to stretch our imagination a little and be willing to accept that time is not quite the steady, universal clock we experience it to be. One of the most profound discoveries of special relativity is that time is relative. It is not absolute. The rate at which time passes for you depends on how fast you are moving. This is a proven fact of our universe, confirmed by countless experiments. For example, the GPS satellites orbiting the Earth have to have their clocks constantly adjusted. Because they are moving so fast relative to us on the ground, their clocks actually tick a tiny bit slower. If we didn't account for this, the entire GPS system would fail within a day. So, time is personal. Your clock ticks at a different rate from a clock on a speeding spaceship. Another consequence is that two different observers, moving relative to each other, can disagree on the order of events. For events that are close together in space and time, this isn't an issue. If I drop a pen, it hits the floor. Everyone, no matter how fast they are moving, will agree that I dropped the pen before it hit the floor. This relationship is called causality. The cause, dropping the pen, must always precede the effect, the pen hitting the floor. The universe seems to have a very strict rule about this. This is the arrow of time. Things happen in a certain order. The past causes the present, which causes the future. But what happens when you introduce something that travels faster than light? Let's build a thought experiment, a famous one called the tachyon telephone. Let's relax and visualize it. Imagine two people, Alice and Bob. Alice is on a spaceship, flying away from Earth at a very high speed, close to the speed of light. Bob is on Earth, standing still. They have a special device, a tachyon transmitter. It can send a message particle, a tachyon, faster than the speed of light. Let's say at noon, Bob's time, he decides to send a message to Alice. He points his tachyon transmitter at her spaceship and sends a signal. Because the tachyon travels faster than light, it will reach Alice's spaceship very quickly. Let's say from Bob's perspective, he sends the message at 12 p.m. and Alice receives it at 12:01 p.m., 1 minute later. Simple enough. But now we have to look at this from Alice's perspective. Because she is moving away from Earth at such a high speed, her experience of time and space is different. According to the strange rules of relativity, from her point of view, the tachyon signal is not just moving from Bob to her. It is also moving backward in her time. When she receives the signal, her clock might read, say, 11:59 A. From her frame of reference, she received the message before Bob sent it. Let's pause with that for a moment. Bob sees the message go forward in time. Alice sees the same message go backward in time. Who is right? According to Einstein, they both are. Reality is what you measure it to be from your own frame of reference. Now, let's take it a step further. As soon as Alice receives the message at 11:59 a.m. her time, she immediately sends a reply back to Bob using her own tachyon transmitter. Again, this tachyon signal travels faster than light. From her perspective, she sends it at 11:59 a.m. and Bob receives it 1 minute later at 12 p.m. her time. But now we switch back to Bob's perspective on Earth, because he is seeing this second tachyon coming from a spaceship that is speeding away from him. He will also see it as traveling backward in his time. He might receive Alice's reply at 11:58 am on his own clock. Let's review the whole sequence from Bob's point of view. At 11:58 a, Ryu receives a reply from Alice to a message he has not yet sent. 2 minutes later, at 12 p.m., he will send the original message that he has already received a reply to. This is a breakdown of causality. The effect, receiving the reply, has happened before the cause, sending the message. Bob now knows what he is going to do in the future. Can he choose not to send the message? If he does, then where did the reply come from? He received a message from nowhere, caused by nothing. This is a paradox. It breaks the logical structure of the universe. It's like a sentence that says, this sentence is false. If it's true, then it must be false. If it's false, then it must be true. It's a loop of logic that eats itself. This is the profound implication of the tachyon. If a stable tachyon exists, and if it can be used to send signals, then the past is not fixed. The future can influence the past. The fundamental chain of cause and effect, the very arrow of time that governs everything from a breaking glass to a star being born, could be broken. It's a concept so disruptive that many physicists believe it's the strongest argument against the existence of tachyons. The universe, they argue, must have a way to protect itself from such paradoxes. Perhaps tachyons cannot interact with normal matter, or perhaps they simply do not exist at all. But the ghost remains, a particle that doesn't just travel faster than light, but travels back in time. The idea that we could send a message to the past opens up a Pandora's box of paradoxes. These are not just fun puzzles for philosophers. They represent deep theoretical challenges to the consistency of physics. If tachyons exist and can interact with our world, then the universe as we know it might become a place of logical contradictions. Let's gently explore some of these paradoxes, not as frightening possibilities, but as fascinating thought experiments that help us understand the rules of our own reality. The most famous of these is the grandfather paradox. It's usually told in a rather dramatic way, but we can frame it more gently. Imagine you could build a machine, a tachyon device, that could send a single bit of information back in time. Not a person, not an object, just a simple message. Let's say you send a message back to your own computer 1 hour in the past. The message simply says, delete this message before it is sent. Your computer in the past receives this instruction, and being a good computer, it follows the command. It deletes the message. But if the message was deleted in the past, then it was never sent. And if it was never sent, it could not have been received by the computer in the past. And if it was not received, it was not deleted, which means it was sent, and so on, forever. We are trapped in a logical loop. The event prevents its own cause. This is the core of the causality violation. It creates a situation that is fundamentally inconsistent. The universe cannot be both message sent and message not sent at the same time. It's a contradiction. Physicists and philosophers have spent a great deal of time thinking about how the universe might resolve such a problem. There are a few main schools of thought. The first and simplest is that such paradoxes are proof that time travel to the past is impossible. This is the view held by many physicists. They would say that the existence of such paradoxes is a strong piece of evidence that tachyons, at least in a form that can interact with us, cannot exist. The laws of physics in this view are self-policing. They contain a fundamental principle that forbids causality violations. The universe has a built-in protection mechanism. The fact that we live in a logically consistent world where causes precede effects is evidence of this protection. We might call this the chronology protection conjecture, a term coined by the great physicist Stephen Hawking. He suggested that the laws of physics conspire to prevent time travel on a macroscopic scale. The universe, he joked, does not allow for time travelers, which is why we haven't been overrun by tourists from the future. A second possibility is more subtle and strange. This is the self-consistency principle, most famously articulated by the Russian physicist Igor Dmitrievich Novikov. This principle suggests that time travel to the past might be possible, but you can only do things that are consistent with the future you came from. In other words, you cannot change the past. Any action a time traveler takes was already part of history. If you went back in time to try to stop the message from being sent, something would prevent you. Perhaps you would trip and fall. Perhaps your machine would break at the last second. The universe would ensure that the timeline remains self-consistent. You have free will to try to change things, but the outcome is already written. You cannot create a paradox because the laws of physics would steer events in such a way that no paradox could ever form. In this view, history is a single immutable block. You can travel within it, but you cannot alter its shape. It's a comforting thought, in a way. It removes the danger of accidentally unraveling reality. But it also raises deep questions about free will. If you can't change anything, are your choices truly your own? A third idea is that of parallel universes or multiple timelines, a concept popular in science fiction. In this view, when you send a message back in time and change something, you don't change your own past. Instead, you create a new branching timeline. In one timeline, the message is sent. In the other, it is not. The paradox is avoided because the cause and the effect exist in different universes. The original universe remains unchanged, while a new one is born from the moment of the change. This is a very clean way to solve the paradoxes, but it comes at a cost. It requires the existence of a potentially infinite number of parallel worlds, something for which we have absolutely no evidence. It is a grand and spectacular idea, but one that is, for now, pure speculation. So, the theoretical challenges posed by tachyons are immense. They force us to confront the deepest questions about the nature of time, causality, and free will. Do the paradoxes mean that tachyons are impossible? Or do they mean that our understanding of reality is incomplete? Perhaps there are laws of physics we have yet to discover that would resolve these contradictions in a way we can't yet imagine. Some physicists have proposed that tachyons, if they exist, might be quarantined. They might be unable to interact with normal matter, radions, in any way that could transmit information. They would be true ghosts, passing through our world without a trace, unable to be detected or used. They would exist in their own separate realm, their causality violating potential forever sealed off from us. In this scenario, the universe could contain faster-than-light particles, but the timeline would remain safe. The ghosts would remain ghosts, and our world of cause and effect would remain intact. The paradoxes they raise are like riddles posed by the universe, and our attempts to solve them teach us more about the elegant and resilient structure of our own reality. So far, we have been talking about tachyons as they appear in the world of relativity, the world of space-time and speed limits. But in the 20th century, a new language emerged to describe the universe at its smallest scales. Quantum field theory, or QFT. This is the theory that underlies the standard model of particle physics, our best description of the fundamental particles and forces. And when we look for the tachyon in the world of QFT, we find something very different, and perhaps even more profound. Let's try to visualize what a quantum field is. Imagine the entire universe is filled with a calm, invisible field. Think of it like a perfectly still, silent ocean stretching out in all directions. This is the vacuum, the state of lowest energy. Now, if you tap on this field, you create a ripple, a little wave of energy. That ripple is what we perceive as a particle. So, an electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. All the particles we know are just excitations, little vibrations in their own underlying fields. QFT is the mathematics that describes how these fields interact and behave. Now, what would a tachyon look like in this picture? In QFT, the mass of a particle is related to the properties of its field. For a normal particle with real positive mass, its field is stable. It's like a marble resting at the bottom of a bowl. It's at its lowest energy state. You can add energy to make it roll around, creating particles, but it will always want to settle back down at the bottom. The bottom of the bowl represents the stable vacuum. A tachyonic field, however, is different. A field that would give rise to a particle with imaginary mass, in the old relativistic sense, has a very strange shape. It's not like a bowl. It's like a bowl that has been turned upside down. Or perhaps more accurately, like the bottom of a wine bottle, with a peak in the middle and a trough all around it. The state of zero energy for this field is represented by a marble balanced perfectly on top of that central peak. This is what tachyonic means in modern physics. It signifies instability. That marble balanced on the peak is in a state of maximum, not minimum, energy. It is a false vacuum. The slightest perturbation, the slightest quantum jiggle, will cause the marble to roll down off the peak and settle into the circular trough at the bottom. This process of rolling down from the unstable peak to the stable trough is called tachyonic condensation. So, in QFT, the tachyon is not really a particle that travels faster than light. Instead, the tachyon is a signal that the system you are looking at is unstable and needs to change. It's a mathematical red flag. It's the universe saying, This configuration is not sustainable. I need to find a better, more stable state. The tachyon itself, the particle balanced on the peak, can never truly exist because it is infinitely unstable. It's the process of its decay, the rolling down the hill, that is the important physical event. This idea of tachyonic condensation is not just a theoretical curiosity. It is one of the most important concepts in modern physics. It is the key to understanding something called the Higgs mechanism. In the very early universe, just after the Big Bang, all the fundamental particles were thought to be massless. They all zipped around at the speed of light. The field associated with the Higgs boson, the Higgs field, was in a symmetric but unstable state. It was like that marble balanced on the peak. It was, in a sense, a tachyonic field. This state could not last. The universe cooled, and the Higgs field underwent tachyonic condensation. It rolled down the hill and settled into a new lower energy state, the stable trough at the bottom. This event is sometimes called the electroweak symmetry breaking. As the Higgs field settled into its new stable vacuum, it filled all of space. And now, other particles, like electrons and quarks, that interact with this field gain a property that we perceive as mass. It's like trying to walk through thick honey. The interaction with the Higgs field drags on them, giving them inertia, giving them mass. So, in this very real and fundamental way, a tachyon is responsible for the fact that we have mass. It wasn't a faster-than-light particle that did this. It was the instability that the tachyon represents. The tachyon was the symptom of an unstable universe, and the universe cured itself by condensing the field, a process which gave birth to the world as we know it. The ghost of the tachyon is written into our very bodies, in the mass of every atom. This perspective also appears in other advanced areas of physics, like string theory. String theory is an attempt to unify all the forces of nature by proposing that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. Different vibrations of the string correspond to different particles. In some early versions of string theory, the mathematics predicted a vibrational state that corresponded to a particle with imaginary mass, a tachyon. For a long time, this was seen as a major flaw in the theory. A theory that predicts a tachyon is predicting an instability. It's like building a house with an unstable foundation. But theorists now understand this differently. The presence of a tachyon in a version of string theory means that the version is not describing a stable universe. It's describing a false vacuum of string theory, which must decay into a more stable configuration. So even in these most advanced conspeculative theories, the tachyon plays the role of a messenger, a harbinger of change, signaling a fundamental instability that needs to be resolved. It is less of a particle and more of a process, a transition from a state of what might have been to the state of what is. With such a strange and provocative idea as the tachyon, it's only natural that scientists would try to find it. Despite its ghostly theoretical nature, the possibility of its existence, however remote, is too tantalizing to ignore. The search for tachyons is a fascinating story of ingenuity, of looking for something that may not be there, and of the rigorous self-correction that is the hallmark of good science. The hunt for these swift phantoms has taken place in the depths of space and in the heart of our most powerful machines. So, how would you even begin to look for a particle that moves faster than light? One of the most direct ways is to look for its signature in high-energy events from the cosmos. Imagine a supernova, a massive star exploding far away. This explosion releases a tremendous burst of energy, sending out all sorts of particles and radiation in all directions. It sends out light in the form of photons. It also sends out other particles, like neutrinos. If tachyons were also created in this explosion, they would travel faster than the light. This means they would arrive at our telescopes on Earth before the light from the explosion does. So one type of search involves monitoring the sky for cosmic events and looking for any mysterious, unexplained particle signals that arrive just before the main event. You would be looking for the opening act of the cosmic show. Scientists have used detectors designed to spot high-energy particles, like cosmic rays or neutrinos, and have looked for such precursor signals. They would point their detectors at known sources of high-energy particles, like pulsars or active galactic nuclei, and wait. It is a search that requires immense patience. To date, after decades of looking, no credible evidence for any faster-than-light precursor signal has ever been found. The universe has kept its ghosts well hidden. Another place to look is in our own particle accelerators, like the Large Hadron Collider at CERN. In these incredible machines, we smash particles together at nearly the speed of light to see what new particles are created from the energy of the collision. Physicists meticulously measure everything that comes out of these collisions, all the particles, their energies, their trajectories. If tachyons were produced in a collision, they would behave in a very strange way. Because they have imaginary mass, their energy signature in the equations would be negative. This might show up as missing energy or momentum in the experiment. The total energy and momentum after the collision wouldn't seem to add up to what was there before. Scientists are always on the lookout for such anomalies. So far, the books have always balanced. The energy accounts have always been settled. No missing energy has ever been reliably attributed to the creation of tachyons. Perhaps the most famous and most human story in the experimental search for tachyons happened in 2011. It wasn't even a direct search for them. It was an experiment called OPERA, located at the Gran Sasso National Laboratory in Italy. The experiment was designed to study neutrinos, which are incredibly light, ghostly particles that barely interact with anything. The scientists at CERN would generate a beam of neutrinos and fire it straight through the Earth's crust to the detector in Italy, a journey of about 730 kilometers. The goal was to study how neutrinos change their flavor as they travel. To do this, they needed to time the journey of the neutrinos with extreme precision. They knew exactly when the neutrinos left CERN and exactly when they arrived in Italy. In September 2011, the OPERA team made a shocking announcement. They had been running the experiment for 3 years, and their data seemed to show that the neutrinos were arriving in Italy about 60 nanoseconds. That's 60 billionths of a second, sooner than they should have if they were traveling at the speed of light. It was a tiny amount of time, but it was statistically significant. It seemed they had accidentally discovered a particle that was breaking the cosmic speed limit. The news caused a worldwide sensation. Headlines screamed that Einstein was wrong. The scientific community reacted with a mixture of excitement and extreme skepticism. The OPERA team themselves were very careful. They did not claim they had disproven relativity. They published their results and asked the global physics community to scrutinize their work, to try and find a mistake. This is science at its best. Not a proclamation of truth, but a humble presentation of a strange result, open to criticism and verification. Other labs around the world scrambled to check the result. For months, the physics world was buzzing. Could it be true? Had we finally found a crack in Einstein's theory? Was the neutrino a tachyon? But as the scrutiny continued, doubts began to emerge. Then, in early 2012, the answer was found. It wasn't a revolution in physics. It was a problem with a cable. There was a faulty fiber optic cable connecting a GPS receiver to the master clock of the experiment. This tiny piece of hardware was not seated correctly, causing a slight delay in the timing signal. This delay made it seem as though the neutrinos were arriving earlier than they actually were. There was also another, smaller timing issue found in an oscillator. When these technical glitches were fixed, the team ran the experiment. The result was clear. The neutrinos arrived exactly on time. They traveled at, or just under, the speed of light. They were not tachyons. The opera story is a beautiful illustration of the scientific process. It shows how an extraordinary claim requires extraordinary evidence. It shows the importance of skepticism, collaboration, and the willingness to admit a mistake. It was a moment of great excitement, followed by a sober correction. And in the end, Einstein's theory emerged, once again, unscathed. The search for tachyons continues in the quiet background of other experiments. But so far, every attempt to find them has come up empty. They remain elusive, perhaps non-existent, a ghost in the machine that has yet to make an appearance on the physical stage. While tachyons may not exist in our physical reality, they are very much alive in our culture and in our scientific imagination. The idea of a particle that can outrun light and travel back in time is simply too powerful to be confined to the pages of academic journals. It has leaked out into the wider world, inspiring stories, shaping thought experiments, and pushing us to ask fundamental questions about our universe. The cultural and scientific impact of this ghostly particle is, in its own way, very real. Nowhere is the tachyon more at home than in the world of science fiction. The moment the concept became popular in the late 1960s, writers and creators seized upon it as a perfect narrative device. It was a scientifically plausible-sounding explanation for two of the biggest dreams of science fiction: faster-than-light communication and travel. In the vast universe of Star Trek, for example, subspace communication is the technology that allows starships light years apart to have conversations in real time. While the show uses its own unique technobabble, the underlying concept is often described as a network of tachyons or subspace particles that are not bound by the speed of light. It solves a fundamental problem for storytelling in a galactic setting. Without it, a message sent from one star system to another could take years, or even centuries, to arrive. Tachyons provide a convenient and cool-sounding shortcut. Similarly, in the television series Babylon 5, a more grounded and politically complex science fiction saga, tachyon communication is the standard for interstellar contact. The show even features a tachyon net that allows for instantaneous messaging across the galaxy. The use of tachyons in these stories, and many others, in books, films, and games, has cemented the word in the public consciousness. For many people, tachyon is simply a synonym for faster than light. It has become a piece of our shared futuristic vocabulary, a testament to the power of a single elegant scientific idea. But the impact of the tachyon goes far beyond providing a plot device for sci-fi writers. In the scientific community itself, the tachyon serves a vital purpose as a thought experiment. It is a tool for probing the limits of our own theories. By asking, what if tachyons exist? Physicists are forced to examine the foundations of relativity and causality with incredible rigor. The paradoxes that Tachins generate are not just problems to be dismissed. They are puzzles that reveal the deep and beautiful consistency of our physical laws. Thinking about the Tachin telephone and the grandfather paradox forces a physicist to be crystal clear about what causality really means. It forces them to appreciate the delicate interplay between time, space, and the observer. The Tachin is like a stress test for our theories. If a new theory of everything, like a version of string theory, predicts stable Tachins that can interact with us, then that theory has a serious problem. It has failed the causality stress test. The Tachin acts as a gatekeeper of sensible physics. Its presence in an equation is often a sign that the theorist has made a wrong turn, that they are describing an unstable or non-physical state. As we saw with the Higgs mechanism, this can be incredibly useful. The Tachin problem in the early electroweak theory was not a failure. It was a signpost pointing the way to a deeper truth about how particles acquire mass. The discussion about Tachins also enriches our broader philosophical understanding of the universe. It brings us face to face with the mystery of the arrow of time. Why does time seem to have a direction? Why do we remember the past but not the future? This is one of the deepest unsolved questions in physics. The standard explanation is related to the second law of thermodynamics, the idea that entropy or disorder always increases in a closed system. A broken egg is more disordered than a whole egg, so eggs break but do not unbreak. This gives time its forward momentum. But a Tachin, by being able to send information backward in time, would seem to violate this. It would allow an effect to precede its cause, scrambling the entropic arrow of time. Thinking about Tachins makes us appreciate how fundamental this arrow is to our existence. Our entire experience of reality, of memory, of choice, of life itself, is built upon this foundation of causality and the forward flow of time. The Tachin, a particle that could undo this, serves as a powerful reminder of how special and perhaps fragile this structure is. It encourages us to contemplate the nature of time itself, not as a simple, ticking clock, but as a dynamic and mysterious property of the cosmos. The ghost of the Tachin may never be found, but its shadow has taught us a great deal. It has inspired our stories, sharpened our theories, and deepened our awe at the logical and elegant universe we inhabit. So where do we stand today? After decades of theoretical exploration, paradoxes, and fruitless experimental searches, what is the current status of the particle that travels back in time? And what, if any, are its future prospects? As we bring our gentle journey to a close, let's gather the threads and look at the Tachin in the cool, clear light of 21st century physics. Today, the Tachin remains a purely speculative concept. The overwhelming consensus in the physics community is that Tachins, as originally conceived, as stable, faster-than-light particles do not exist. There is not a shred of experimental evidence to support their reality. Every test of special relativity has confirmed its predictions with stunning accuracy. The cosmic speed limit appears to be one of the most robust and unshakable laws of nature we have ever discovered. The theoretical roadblocks, particularly the profound problems with causality, are considered by most to be insurmountable. The universe just doesn't seem to be built in a way that allows for grandfather paradoxes or Tachin telephones. The chronology protection conjecture, the idea that the laws of physics forbid time travel, seems to hold true. Furthermore, as our understanding has deepened with quantum field theory, the role of the Tachin has shifted. As we've explored in modern physics, A tachyonic field is understood not as a source of FTL particles, but as a sign of an instability in the vacuum. The tachyon is a mathematical artifact of a system that is out of balance, a system that must decay into a more stable state. In this modern context, tachyons have already played their part. They drove the Higgs mechanism, giving mass to the universe. They signal problems in speculative theories, like string theory, guiding theorists toward more stable models. In this sense, tachyons are less of a futuristic possibility and more of a ghost of the universe's past, a relic of a transitional phase that happened long ago. They are a tool for understanding how the universe became the way it is, rather than a particle we might one day harness. So, is the story of the tachyon over? Is it destined to be a footnote in the history of science, a curious idea from the 20th century that turned out to be a dead end? Perhaps, but physics is a constantly evolving field. Our understanding of the universe is still incomplete. There are vast mysteries that remain unsolved, and it is in these dark corners of our knowledge that speculative ideas can sometimes find new life. One such mystery is quantum gravity. We have two incredibly successful theories of the universe: general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes the bizarre world of particles and forces. But these two theories are fundamentally incompatible. We do not yet have a working theory of quantum gravity that can describe what happens when extreme gravity meets the quantum world, such as in the center of a black hole or at the moment of the Big Bang. It is possible that in a future theory of quantum gravity, our understanding of spacetime, causality, and even time itself might be radically altered. In such a theory, could a concept like the tachyon be reborn in a new, more sensible form? It's impossible to say, but it is in these frontiers that the truly revolutionary ideas will be found. Similarly, theories like string theory or other theories of everything continue to evolve. While tachyons are usually seen as a problem in these theories, some speculative models have explored the idea that tachyons might be confined to extra dimensions of space, unable to enter our own, or that their paradoxical effects are somehow canceled out of unknown quantum phenomena. These are highly speculative and mathematically dense ideas, far from being testable. But they show that the spirit of what if is still alive. The search for the tachyon, even if it has been unsuccessful, has not been a waste. It has been a valuable and illuminating quest. It has forced us to test the limits of our most cherished theories. It has sharpened our understanding of causality. It has given us a language to describe fundamental instabilities in the universe. And it has fired our collective imagination. The tachyon is a perfect example of a beautiful scientific idea. A beautiful idea does not have to be true to be useful. The concept of the ether, the invisible substance once thought to fill space, was wrong, but thinking about it led to the development of relativity. The model of the atom as a tiny solar system was wrong, but it was a crucial stepping stone to our modern quantum understanding. In the same way, the tachyon may be destined to remain a ghost, a whisper of a possibility in a set of equations, a swift phantom that outruns light in our imagination, but not in our reality. But its legacy is real. It is woven into our stories, our science, and our unending quest to understand the cosmos. The particle that travels back in time may never be found, but thinking about it will always propel our understanding of the universe forward. And as you drift now into the gentle currents of sleep, perhaps you can imagine this little ghost particle, not as a paradox, but as a symbol of our own restless curiosity, a curiosity that will forever race ahead, faster than light, into the great, beautiful unknown. Good night.